Hello everyone, in this video we are going to discuss a really good problem, little elephant and introvert. You can pause the video and read the problem. This problem is available in Codeforces and we will be given two integers which are in between these two numbers 1 and 10 to the power of 18, L and R. We need to find integer x or number of such integers x such that their first digit and last digits are similar. For example, we can has given few examples here. See the number 101, the first digit is 1 and the last digit is 1, so it satisfies that property. See another number 477474, first digit is 4, last digit is 4. See 9 starts with 9 and ends with 9. So not only 9, every single digit number satisfies that property. You can also see numbers which violates that property. Now let's clearly see how to approach this problem. So guys, you had a glance at the problem statement. Now let's see the step-by-step procedure to solve the problem. We are given L and R as input, where L and R are integers such that they are upper bounded by 10 power 18. So we can use long data type to store these values. What we need to output is the cardinality of set A, where A has all numbers x such that these two conditions are satisfied, as mentioned in the question. So let's see how to approach this. Firstly, let me explain few test cases. We are initially given 2 and 47. 2 is L and 47 is R. Now we need to output number of integers from 2 to 47 such that their first and last digits are same. You can simply break down this to denotes number of integers from 0 to a number x that satisfies the given constraint. Then for this input, we can say that answer would be f of 47 minus f of 2 minus 1, because if we know the answer for 1, that is 1 less than 2, and for 47, suppose this denotes the range for 0 to 47 and this denotes the range from 0 to 1. If we subtract this from this one, then we simply get the answer from 2 to 47. So what we need to do is we need to make a function f such that it says this thing. See the steps one after the other. First one is take L and R as input. Second one is decrement L. Third one is let equals to f of R. Let p equals to f of L. Then we just output A minus B. This is simply the pseudocode for the above problem. Let's see how we can make this function for a given number. So what this function does is it takes the number as input and it returns number of integers, or let's say number of whole numbers whose start digit and end digit are same and are less than this number. Let's see how we can do this. Since you got an intuition from the above code that we need to use some kind of recursion, let's see how we can approach this. To understand this, simply build the recursion for small test cases. Like suppose if you take 1, that is the number equals to 1, then How many whole numbers are there such that their start and end digits are same? There are only 0 and 1 that are less than or equals to this number. So the output would be 2. So f of 1 equals to 2. If we take number equals to 10, then how many whole numbers are there that are less than or equals to 10 and whose start digit and end digit are same? They are 0, 1, 2, 3, 4, up to 9. Total 10 numbers. So f of 10 equals to 10. For 100, we know that until 10, there are 10 whole numbers. So we need to look from, since 10 does not satisfy this property that was mentioned in the question, we need to narrow down our search space from 11 to 100. Since we already know from until 10 how many whole numbers are there, we just have to find these and add to f of 10. So from 11 to 100, we have 11, 22, 33, 99. These are the numbers whose start digits and end digits are same until 100. And 100 does not satisfy the property that was mentioned in the question. So from 11 to 100, there are 9 numbers. Until 100, there are, since up to 10, there are 10 numbers. From 11 to 100, there are 9 numbers. Up to 100, there are 19 numbers that satisfy the property mentioned in the question. So f of 100 would be, let's look at 1000. We know from 0 to 100, there are 19 numbers. Now, since 100 does not satisfy the property mentioned in the question, we need to look from, so let's see all the possibilities and count number of search integers from 101 to 999 that satisfies the property. What property tells is if the first digit is 1, then the last digit should also be 1. If a number is in this form, in how many ways can we fill the middle place? We can fill it by 0, 1, 2, or 9, like 101, or 111, 121, 191. There are actually 0 to 9, 10 possibilities are there. So if the number starts with digit 1, there are 10 possibilities. It cannot start with 0 because that would be a two-digit number. We already accounted for two-digit number by considering numbers until 100. We are only considering three-digit numbers from 101 to 999. So we start with 1. Let's see how many numbers are there starting with 2. The same logic. It should, since it has to satisfy the property mentioned in the question, it has to end with 2. And we can fill the middle value with 10 possibilities. So there are 10 such numbers like 201, sorry, 202, 212, 222, and 232, so on 292. There are 10 such possibilities. Same for 3 until 9. So, so until 1000, there are 9 into 10. From 101 to 999, there are 9 into 10 such numbers. From 0 to 100, we have 19 such numbers. So above 1000 equals to above 100 plus this 9 into 10 equals to 9 to 10 plus 19. This is until 1000. Let's multiply the 1000 by 10 and see the number of possibilities. Let's see how many numbers exist until 10,000. Why I'm doing this, why I'm multiplying each number by 10 is because we are incrementing number of digits in the number by 1 every time we multiply by 10. So until 1000, we saw all the one digit number, two digit number, and three digit numbers. Until 10,000, we cover all the one digit, two digit, three digit, and also four digit. Even though this is a five digit number, every number below this are at most four digit numbers. So let's say for 10,000. Since we know until 1000, we just have to find from 1000, 1 to 10,000. Since 10,000 does not satisfy the property because last digit and first digit are not similar, we just have to find from 1001 to 9999. So now we are looking at four digit numbers. Remember, the first digit cannot be 0 because that would be a three digit number. We are only looking at four digit numbers as we have already covered three digit numbers earlier. So if you consider the first digit to be 1, the last digit also has to be 1 to satisfy the property. And let's see the possibilities here. I can fill this place with 10 digits. that is 0, 1, 2 until 9. 10 possibilities are there. Here also same 10 possibilities are there. So there are 100 such numbers. So a 4-digit number starting with 4-digit number starting with 100 such 4-digit numbers are there. The same if the first digit is 2, 3 until 9. For each one we get 100 such numbers. So total 9 into 100. So from 1001 to 9999 we have 900 such numbers. So f of 10,000 would be f of 1000 plus 9 into 100. So f of 1000 is 19 plus 9 into 10. You can observe one relation every time we increase the number of digits, that is until 10 we got 10 such numbers, that is 1 plus 9, 1 is for 0. Until 100 we got this 10 plus 9. Write this as 10 power 0 since 10 power 0 is already 1. This is just to see the pattern in it. For 1000 we have 10 plus, this is for 1000. For 10,000 we saw number of such numbers we saw number of such 4 digits are 900. 900 can be written as 9 to 10 square. So there are 4 zeros here, and what we are doing is let's say uh, p with a function. It takes I as input, and it tells us number of such numbers satisfying the property from 0 to 10 power I. We saw if we fill p of 0, that is until 10, as the value as 10, then we can from and p of 1 as 19, that is 1 is simply from, every time we increase the number of digits we could see a pattern. I will explain this by considering a function p that takes I as input. And what this function produces is tells us number of numbers from 0 to 10 power I that satisfies the property mentioned in the question. That is, the first digit and last digit have to be equal. If we start from I equals to 0, for I equals to 0, that is from 0 to 10 power 0, 1, how many numbers are there? 2, that which are 0 and 1. For I equals to 1, that is from 0 to 10 to the power of 1, that is 10, we have 10 such numbers. These are the base cases, and now we can proceed from for I equals to 2. We can say number of such numbers from 0 to 100. You can clearly see here that we borrowed this 10 from here. So we can say p of 2 equals to p of 1 plus 9 into 10 to the power of, we can say 2 minus 2, right? So overall the recurrence relation would be p of I for I greater than or equals to 2 equals to p of I minus 1 plus 9 into 10 to the power of I minus 2. Since we cannot write for p of 1 directly on the basis of recurrence relation, that's why we kept 1 in the base case, since we cannot write 1 in place of I here. So p of 0 comma p of 1 would be priorly filled, and we put them as base cases. So overall we have to get until 18 because L and R are less than or equals to 10 to the power of 18. If we know number of such numbers until 10 to the power of 18, if we know number of such integers from 0 that are satisfying the above property, then we can solve the problem easily. So Before entering into the procedure, we pre-process and make this DP array, which is this for every problem, so that it would be easy later to calculate. Let's see how this helps us later. Until now, we have seen numbers like 0, 1, 10 squared, 10 cubed, so on, which are 10 to the powers. Let's see how these things help. Let's take a number. Let's take a sample input. 2 and 47. L and R. First thing we need to do is decrement L. That is 2 minus 1 equals to 1. For 1, we directly know which this is already stored in the array. Number of integers from 0 to 1 that are satisfying the property are 2, which are 0 and 1 itself. For 47, we need to find out number of such integers from 0 to 47 satisfying the property. Let's see how, by using the DP array that we made in the pre-processing step, we can solve this. Whatever the number will be given, okay, whatever R be or any number, just see number of digits in it, okay. Since there are two digits here, decrement that number, store this in a variable d, which denotes the number of digits in the number, decrement d by 1. Now d equals to 1 for 47, and look in the DP array for 1, that is number of integers from 0 to 10. We know that the answer is 10. Now, since you have covered from 0 to 10, we are just yet to cover from 11 to 47. That is, you know that from 0 to 10, there are 10 such numbers. All you need to find out is from 11 to 47. Why why this distinction helped us earlier is, look 47. Look at 47. If you want to apply permutations or something like that, you can. It's simple to apply on two-digit number rather than considering single-digit numbers too. Suppose for 47, you can say the two-digit numbers that satisfy the property are 11, 22, 33, and 44. You don't have to care about the one-digit numbers. You just have to only care about the two-digit numbers. So for 47, the answer would be 10 from 0 to 10. From 11 to 47, there are four such numbers. These four, so 14. The answer for 2 and 47 would be this subtracted from this. This has to be subtracted from this. So 14 minus 2 equals to 12. That is the answer. Now, this looks like easy for a simple two-digit number. Let's see for a four-digit number. Let's take another sample input. 47 and 1024 as mentioned in the question. In the previous question, we saw a number of integers from 0 to 47 that satisfy the property mentioned in the question. There are 14 such numbers. We need to figure out for 1024. Okay. For 1024, there are four digits. In 1024, since there are four digits, we only consider all the four-digit numbers that satisfies the property mentioned in the question and are less than or equals to 1024. You don't have to worry about three-digit, two-digit, or one-digit numbers because that are already calculated and they are available in TP of 3, that is 10 cube, 1000. we know number of such numbers between 0, sorry, from 0 to 1000, we just have to calculate from 1001 to 1024 how many such integers are there. From 0 to 1000, we calculated earlier that there are 109 such numbers. If we know number of integers from 1001 to 1024 that satisfies the property, then we just add to 109. So from 1001 to 1024, it is a 4-digit number, and if the first digit is 1, then the last digit also has to be 1, and in between we can fill these two places cannot be filled with 10 into 10 possibilities, because if you fill 1111 two ones in those two places, then this number would be greater than 1024, and that violates the property. So we just have to take care that the number should be less than 1024. Since this digit is 0 in 1024, we don't have any choice but to fill this as 0 itself. We only have choices for this place. So since this digit is 2, we can fill with 0 or 1 or 2, because 1001 and 1011 or 1021, they're all less than or equals to 1024. So we got three such numbers from 1001 to 1024. We just add. So there are 109 plus three such numbers for 1024, and for 47, remember that we have to decrement it first. 46, from even 0 to 46 we have 14 numbers, because 47 itself violates the property, so it doesn't matter even if you decrement it. Answer would be 98. I can understand that this is still confusing, as I did not explain the exact logic for numbers other than 10 to the power 2 or 3 or 4. Let's see it clearly. Let's take an example like 8, 1, 3, 2, and 5. Let's take another example, 8, 1, 3, sorry, 3, 2, and 9. Remember these two examples, and let's see for each of them the number of possibilities. As usual, you count the number of digits in this number, 1, 2, 3, 4, 5. There are 5 such digits. Decrement D. Now D becomes 4, and look in the DP table, DP of 4, which is DP of 10,000. You store them in a variable, keep it aside. Now you know all 0, sorry, 1, 2, 3, 4-digit numbers. So you know all the 4-digit numbers that satisfies the given property. You just have to find from 10,000, 10,001 to the given number, 81,325. Observe this number carefully. The first digit is 8. So if you replace the first digit by 1 or 2 or 3 or 4, 5 or 6 or 7, those numbers would still be less than 81325. That is like 11325 or 21325 or 31325 or 71325. They will still be less than the number. So you can fill the first digit with any of these numbers and check how many such numbers are possible. For example, you can fill with 1. Remember that we cannot fill with 0. Why? It was mentioned many times before that if you fill it with 0, the number would become 4-digit number, and we already took care of that number by counting until 10,000. So you start with 1, since the last digit should also be 1. No matter whatever you fill in these three places, that number will still be less than this number and satisfies the property. This can be filled with 10 digits. There are total 20 possibilities are there for a number starting with 1. The same goes for number starting with 2 until 7. So there will be 7 into 10 cube. Now let's see what happens when we fill the first digit with 8. When you fill the first digit with 8, you cannot fill whatever you want in these three places, because if you fill 9 here, you fill 0 here, you fill 0 here, it will be greater than the given number. This one is 81,000, this one is 89,000. So you have to take care of these conditions. Let's see how. If you have 8 here, then you can fill these three digits with 000 or 001 or 002, because these values are less than 81,325 until 131. 81,000, sorry, 81,318 is still less than 81,325. So for the given number, if you exclude first digit and last digit and look at the middle number, if you keep 132, then 81,328 would be greater than 81,325. So you cannot go until 132, you can go only until 131. So there will be from 0 to 131, there are 132 numbers. So 132 are possible. So the answer would be TP of 10,000 plus this. Now let's look at another number as discussed earlier, 81329. Number is 81329. As discussed in the first example, you look at 8, you can fill the first digit with any number that is less than 8, because that number would still be less than the given number. If you can fill it with 1, 2, 3, so on, 7. Now it's 7 into 10 cube. Now let's see what happens when you fill this with 8. And middle numbers are 1, 3, 2. You can fill this with 0, 0, 0, 0, 0, 1, so on, 1, 3, 1. That 81,390 would still be less than the given number. If you start filling with 132, you can observe that it will be still less than or equals to the given number. That is not a problem. So that is okay. Few In the previous example, we went until 131. We did not go 132 because that violated the property. Now, if we go until 132, the number would be 81328. First digit and last digit, sorry, this should be 8. We fill the first and last digits as 8. We went until 132. You can observe that 81328 is still less than the given number by one number. This is just one less than the given number, but it still satisfies the property. So we can go until 132. So total 133. That is from 0 to 132. There are 133 such numbers. So for this, the answer would be TP of 10,000 plus 10 plus 133. So that is how you proceed. Simply put, whatever the number looks like this, and you just take dp of n into a temporary variable, and as discussed earlier, look at the first digit and subtract or subtract that by 1 simply, and take it into a variable t equals to a1 minus 1, and you see number of intermediate digits which are n minus 2. So we multiply a1 minus 1 with 10 to the power of n minus 2 as we did here. First digit is 8, so we went from 1 to 7 and multiplied it by number of intermediate places they rise to the power. This is n minus 2 because we excluded first and last element because they have to be the same and we don't have any uh, as many choices as the intermediate places. Now we went from 1 to a1 minus 1. Now while filling a1 at the first digit, we only go from 0 to a2, a3, an minus 2, minus 1. When is this possible? When an, that is the last index, is less than a1. Okay, we go from 0 to a2, a3, an minus 2 when an is greater than or equals to a1. You can see the above examples. This is the initial number. This is a1. This is a n. We saw that a1 is less than or equals to an, so we could go until 132. For the previous number 81325, this is a1, this is an, and we could go only until 131 because a1 is greater than an. That's the simple logic. And 0 to a2, a3, so on an minus 2 minus 1. There are a2, a3, an minus 2 such numbers. For here, there would be a2, a3, n minus 2 plus 1 such numbers. There will be an extra number in this case. That is the number itself, the intermediate number itself. So this is the overall logic. Now let's see the code. Now let's see the coding part for the solution discussed earlier. We, as discussed earlier, the constraints on the numbers are up to 10 to the power of 18. So we declare them as long instead of integers, and we take two vectors va and vb, and what this make vector function does is it takes each digit out of the number and push it back into the array, sorry, into the vector. Let's see how this make vector function works. This is how it works. It simply takes out each digit from the vector and it simply takes each digit from the number and push it back into the vector a. We do this so that later the calculations will come in handy and also will be easy for you to understand. You can also do this without using a vector also. As discussed earlier, we have a dp vector which stores number of integers from 0 to some 10 or 100 or 1000. We have 19 elements in this dp array where each element representing the number of integers from 0 to 10 to the power of I, where I is the index in the vector. As discussed earlier, for 10 to the power of 0, that is 1, there are two such numbers, 0 and 1, and dp of 0 and dp of 1 are base cases. What this make dp is going to do is, this is a pre-processing step before applying our functions that calculates the answer. We should make sure that this dp array is ready. So let's see what make dp function does. It iterates from 2 to 18th index, and as discussed earlier, this is the recurrence relation that it's going to apply. Uh, now that we have finished all our pre-processing steps, taking input, making the dp vector, let's see the main function find until. What find until does is, uh, in the pre-processing step, we have stored each digit of a number in the vector. So by finding the size of the vector, you will come to know number of digits present in the number. So what we do is, if it is a single digit number, then we simply return a of 0 plus 1, that is the digit itself plus 1, because we consider 0 as a valid number, so we will add 1. If not, then what we do is, we take dp of n minus 1 into a temporary variable sum. dp of, all of this was discussed earlier, and while pushing each digit of the number into the array, the element which is present at the last index of the array will be the first digit of the number. That's why we took a of n minus 1 instead of a of 0, because while pushing into the array in this function, the make vector function, you can take a sample test case and see how elements will be pushed into the vector. All these steps are similar to the ones discussed earlier. Solve the pseudocode, and this step simply tells us that if a of 0, that is the last digit of the number that is present in the first index of the vector, okay, so the last digit of the number, if it is greater than or equals to first digit of the number, then we can consider the middle number itself. So we increment the product by 1. Product simply takes the middlemost digits value. We finally return uh, this sum, which is dp of n minus 1, and the product, which is about the number of integers occupying the middlemost digits, and temp is simply the number which is a of n minus 1 into 10 to the power of n minus 2, that is fine until. So why we